Before we dive into hierarchical models, we'll look at the basics of regressions, slopes, and intercepts. I'm reviewing them so that we use the same terms. If these are new, I suggest the DataCamp courses on regression modeling, like Multiple and Logistic Regression by Ben Baumer. I use the terms linear regression and linear model interchangeably. In the most basic model, we examine the mean across all groups. The name for this term, beta, is the intercept. We also include an error term, epsilon. For the models with multiple intercepts, we can structure the model two ways. First, we can use a global intercept beta naught and then model the effects of groups 2 and 3 compared to the global intercept. Second, we can model each group as its own intercept. Each modeling approach can be helpful depending upon the situation. If we are interested in estimating how two different treatments differ from a reference, we can use the first approach. Conversely, if we are interested in estimating the mean of each group, we can use the second approach. Also, this model is essentially an analysis of variance, ANOVA. In R, the base function LM builds linear models. The syntax includes a formula and data. This linear model could be described as Y is predicted by X using the data, my data. Also, to run an ANOVA, we can wrap the linear model's output in the ANOVA. You've now seen how intercepts can be used to build a linear model for a discrete predictor variable. Now, we're going to look at using continuous predictor variables, slopes. The most basic regression includes a response variable y, an intercept beta naught, a slope beta 1, and an error term. The slope predicts how the expected value changes because of the continuous predictor. The simple linear regression expands to include multiple response variables. These include discrete predictors with corresponding intercepts, as well as continuous predictors with corresponding slopes. The DataCamp course on multiple and logistic regression covers these in greater detail. Multiple regression is a powerful tool, but has limitations. First, predictor variables can change the estimates for other predictors if both are not independent. Small deviations from this can cause quantitative changes to the model if parameters are added or dropped from the model. Large deviations can cause qualitative and statistical changes to the model. Second, the previous consideration requires us to say estimates have been corrected for other variables. Third, Simpson's paradox means missing important predictors can make our model wrong. Fourth, multiple regression assumes linearity. Fifth, we may need to consider interactions, which occur when groups have different slopes. We'll look at interactions in the next exercise. Using linear models in R is relatively straightforward, but has some quirks. First, A minus 1 is needed to estimate an intercept for each group rather than the intercept relative to the first group. Second, if a predictor X is numeric, R treats it as a slope. Fix this by converting predictors to factors. Third, predictors may need scaling. For example, if one predictor is in centimeters and the other in thousands of centimeters, using km or kilometers for the second predictor would be more appropriate. Also, when using time for a slope estimate, you may want to rescale and use 0 for the start. Last, a shortcut for an interaction is x1 times x2 rather than using the plus colon syntax. In this example, we ran a linear model. Then, we extracted the coefficients using the tidy function from the Broom package. Last, we added it to a ggplot. Notice how we extracted the intercept and slope and used the geom AB line function. I did this rather than adding a linear model with geom smooth because this approach extends well to complicated models. Now, it's your turn for regressions.